So let's continue. So now we have looked at skeletons and see how things are branching. Let's put the focus on having more small items. And now we're looking at, for example, grain distributions or other things like that. Could be cell distributions. And the problem is we want to label these items, objects, in some way. When you do the component labeling, you saw that things sometimes are touching and they will appear as a big one. So now we want to see how we can get all items really identified. And that can be done with the help of, let's see, is that off? Ah, there it is. And so a lot of Kaggle competitions that are about just identifying grains from different types of microscope images, soil images, whatever. And in this case, they want to do and it appears that they did a lot of machine learning, so they run some kind of UNet model and to identify different objects, but still they didn't come with that. So that's quite a long recipe. But in the end, they just make a final clause like they did Watershed and some morphology for post-processing to get the right labels in the end. So Watershed is an algorithm that comes out very often, and it's quite a nice method because it really identifies the objects. So looking back again at this cell image, we have some microscope picture here, converted into grayscale. We did some segmentation. Turned out pretty good, but not perfect. You can see here by eye. This one would rather be a cluster of objects, but here you can see that, well, it didn't come out that well. And according to the ground truth, it should look like this. The object is marked up, and I don't even agree with the ground truth, or the color map at least, because you can see here, for example, they are touching, and forming strange shapes. If we try to run a component on this, it would give us essentially only two objects. And this is just a little crop from the microscope image where we have, ideally, according to the ground truth, we should have 4 items here. But if we run the component labeling, we get only 2. And one reason that we get only 2 is that this one up here in the corner wasn't even captured by the segmentation. So that is a loss before we even starting looking at the items. But these 2, they are counted as a single one. And that is our problem now that we want to address. And the Watershed algorithm is as with an analog to the water flowing downhill in the mountain area. And we have the ridge of the mountain, and if you put it will run down into one of the valleys into catchment basins. And in our case, we create this landscape with the help of a distance map. So what you see here is actually the distance map of the cell image extract that we did before. And even with this nice color map, we can get it looking like a landscape. That's just coloring, and it happened to be very nice. But what we are looking for now is a way to separate the 2 items. We have one item here with one catchment basin and one item over here with another catchment basin. Actually, we have the last one over here, but a distance map. So what we need to do as a preparation is we need to first segment the image into a bi-level image, then compute the distance map, and we have to localize in this distance map, we have to identify local maxima. What from scikit image feature, peak local max, which actually identifies the top positions in the image. And we need this case. So to get our starting points, we compute the local max of the distance transform of the black and white image. And afterwards, we get an image looking like this, where we have our segmentation. That was step 1. Then we do the distance map, and you can see that we have some nice distances in it, and also in this corner. And local maxima identifies 4 zones, 4 maxima, one here, 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 and here. These were also labeled, and the reason for labeling them is to provide the label of the region afterwards. So these local maxima will be used as seeds for us filling up the landscape. And each label here would be the label of a catchment basin. Now let's run the watershed. And what it does, it actually separates the 2 large regions and this one, but we get another region in here. And the region is a saddle point in the landscape. So if we go back, oops, that was too far. We have this would correspond to label 1, that would be label 3, that would be label 4, and the 4th point, or actually label 2, is the saddle here between the 2. And that is clean out. And the way to do it, so here, is to look at the size of these found regions, or the values of them. And here we need to do a little bit of coding. So going through here, looking at the area of each region, and if the area is above some criteria, then we use it. And afterwards we get a little list here that tells what we're going to keep and what we're not going to keep. And you can see here that area of label 1 is 82. That's true. Okay, let's keep it. From area 2 is 7, so it's below our threshold, which we set somewhere as some percentile. Okay. And then the other 2 areas, they're also quite large, so we also keep them. And when we reject this area from our segmentation, we come up with a much better result. And that is coming here. Now we have our local maximum map, giving 1, giving 3. And now we have a that is can give us. I need to use a different method, maybe something like called tools that also includes some shape controlling constraints in the model. But with Watershed, you can get to here, which gives us a little bit error. This one we couldn't get anyway. And now let's see what happens when we scale this up. looking at the whole image. Have the whole code here. I'm not going to review it much, but in principle, what we do is we segment into black and white. We do the distance transform, identify peaks and label them, run the watershed, and then we do some size sorting. And here you can see that at 10% cutoff, we removed 25 components from this, which were probably two small objects or also saddle points. And the result from the watershed is this. Doesn't look really convincing. This is the problem with Watershed, that it usually over-segments. The reason is that no, okay, that was what I said. One thing is that we have missing objects. That is how we do the segmentation. Now we used Otso. Maybe we need something smarter to do the segmentation. And the other one is the over-segmentation. And one reason is that we have irregular shapes. They are not perfect rounded objects. And each little notch in the surface produce a little bit distance map, which in turn can produce a lot of local maxima in the distance map. Yes?
So thinking if you, before you use the watershed, can you improve the contrast of the image so that it can miss less objects? Can you do that?
Yes. So one thing is, as I said, we can change the way how we do the segmentation. Here I just used a very simple thresholding technique. Maybe you need some smarter way to do it. And the other one would be to do morphological opening and closing to smooth the surfaces. And also the effect what we saw here, I can see here, is this is what we would completely different distance map. So and the watershed would split this object into two pieces. So the way to use is, of course, pruning, cleaning the images before you compute the distance map. And the other one is also to say smooth the presence of this. Oops. Oh, come on. Smooth this presence of by cleaning up the images before you compute the distance map, or maybe even do some smoothing on the distance map, you can reduce this.
Also with the skeleton, I think if you smooth the
So you may move relevant these kind of modifications. On one side, you do something to remove an effect, but you may introduce something new. So that is something you have to be very careful when you design your analysis, that you don't introduce new things, invent effects. But anyway, what we can do, there are different ways. One is proposed in who first give identify the disconnect those objects with low amplitude peaks. With that, I see. Maybe I can do it with the pen here. Nope. I thought I could do it with a pen. I can't. Okay. So the idea is that if you have, let's just do a one-dimensional profile. So let's look at the profile across the ridge of one object. The local maxima may look like something like this. Then you can say that if the fluctuations between the small peaks is too small, then all of them belong to the same. And that is what is proposed here by Sewell, that identify where the local minima variations are small and bunch them together with the help of as a single local minimum or local maximum, depending on how you flipped the map. And that is done with a method called reconstruction by dilation and erosion. And they are kind of a iterative erosion and dilation algorithms that smooth out and identify local maxima and minima with a certain depth. By doing that, we can do here, calling a function called h maxima. And the function of the h maxima is saying that please give me all the maxima which has the height, local height, at least some value. In my example down here, oops. So look at my map, my distance map, and we had the peak local max was giving us these 4 points. That one was the bad one. And if I say use hmax 2, then that one is actually cleaned out by that. So by doing this, we don't have to do a pre-segmentation and analyze the areas and then come back another watershed. This one is already a preconditioning of the distance map in a way that it rejects more of these unwanted maxima. And this is the way the function looks like. This h min or h max, and that is no, it's markers. Sorry, is in principle if you out all the still have a big one, and that is the idea behind this. I actually had to write this because it's not available in a scikit image, so I had to write it, and we can use it now. And the effect is as follows. We have our color map, where we have distance map, where we have the two catchment basins or 3 catchment basins, and with the watershed method 1, that we had to reject our volumes, which were too small. We came to this value, to this result. If we do min impose, the first thing you may notice is that the distance map has a little bit different shape. So the mountain area here is a bit wider, and also on the positions of our markers, we are much, much deeper. And that gives us this kind of watershed segmentation, which is, in this example, actually exactly the same. But If we now go on to looking at the full image, doing the same thing, you can see now that with method 1, we did that kind of segmentation, and with method 2, we get this. And now it's a bit weird, actually, because you can see that the color of these is the same. The reason is that our color map cannot resolve so many items. So now we need to do something about that to see what we actually have. So looking at the different color maps, we can use, for example, the Viridis, which is linear. You can see that there's a gradient, but still it's hard to visibly distinguish them. Then we have tab 10, which is a discrete map. And you can see, okay, there are many of the same. Tab 20 is also a discrete map, but it also has a problem that it doesn't really identify all the items. So what we need to do to really show how nice we segmented, we need to create a different color map. And is to use either a random color map, so we really randomize all the colors. Each item has its own color, which is random. And I actually also orthogonalize it a bit so it gets really separated. Or the other one is using the golden ratio to determine the next color. And now we can look at what these two color maps look like. Tab 20, as we saw before, has a lot of same color, random, nicely extracts it. And with the golden ratio, we can now see really a nice separation between all the colors, between the objects, and it's much easier to work with, this one. Now, still, it's the light here makes it difficult to distinguish colors, but I think either the golden ratio or the random gives us the best way of showing many items in when you your own code, because otherwise you don't know if you do right or wrong. In the end, you may even use one of these for your publications. Now, as a last example, I would like to show some data that I did. So the exact workflow here is not the same as in the publication, but I learned more on the way, so I have new approaches. What we do have is a problem with two types of sand grains with different size distributions. The volume is 500, 500, 300 pixels big, and the idea studied is at interfaces between different grain size distributions. And what we wanted to do is to identify where we have separation between these two sand fractions. The workflow is first we need to load the data. Then we did some image preparation. That would be noise reduction. We would do binarization, clean out some misclassified voxels. Then doing labeling of the grains. So here we used the Watershed, where I computed a distance map, identified grain peaks, and used the Watershed segmentation. And the second part, now we can come to the analysis. We want to categorize the grains by computing region properties, maybe remove some unwanted items, tiny and huge regions, and then we can inspect the region properties and do some clustering to identify which grains belong to what. And then finally assign back which class belongs to which grain. So we do a little bit of cheating. So I skip the first two steps. So the image preparation and labeling of the grains, I skip those, and we go directly to the labeled image. So we have here a bi-level image. That is our input data. We have also the watershed segmented grains looking like this. And then we can compute from there. We can compute the region properties, and I present them in a data frame. So we do the region props to table, and what I want is the label, I want the area, I want the centroid. And then we can plot already a quite good reduction in data amount. So we had this image, which are some megabytes large, and now we only have a table with some text entries. So this makes it much faster to work with the data, and now we can do more efficient analysis. And first we want to look at that's when I need to run. The table, and we can see in the table that we have a lot of labels. We have the centroids, they don't tell so much about, so they tell of course the position. But the interesting thing is to look at the minimum size of the area and the maximum size, and we see there is a huge span from 1 pixel to almost 3 to the 10 to the 7 pixels in the largest. But in between, we have mainly sizes in the order of 10,000, 30,000 pixels. So that means we have some extremes and a local ring around the information. And essentially what the large one is the pore space, just the background. So that is not relevant. And the small ones, I would say, are misclassifications. So they are also not needed. So what we do is to do some filtering on the table. We have here the foreground pixels, say all the items with area less than 10 to the 7 belong to the foreground. Then we also know that grains that are smaller than 1,000 are not needed. So that creates us now a table with 2 new entries, Boolean entries. And then the final thing is to create a table with only the grains. And just extract that where the foreground is true and small is false, and copy them. As the description of that, we can see that our grain sizes now range from 1,000, because we actually set that threshold. Sorry. Now we have a more reasonable range of sizes, and I believe this is what we will work with. And now looking at the volume histogram, we can see that the main volumes are distributed around very low value, something like no, this is this one is very big. That must be a double so misclassification. But we have the most are down here, around 5 till 30,000, and then we have some larger items. And if you're squinting your eye, able to see that we have 2 distributions here. One distribution with very small items, and one distribution which is wider with larger items. Looking at the centroid, we can do a scatter plot, and you can see that in one part of the image we have centroids that are densely packed, and in one part we have more sparsely distributed items. And that actually makes sense because we have large items and they not be close to each other. We have small items that can be closer packed. Centroid distribution. And we can also use pair plot and looking at our data. And the information we see here is, again, the histogram for each type. The label is kind of useless to look at the histogram because it's just a linear distribution and it shows up. But looking at the label versus the area, you can see that we have, for labels with low values, we have typically smaller objects than labels with larger values. Which is kind of natural because our labeling starts from the top or bottom, segment object to distribution packing. Then of course, if we start from one side going down, we have the typical small distribution, and then all of a sudden we come to the large distribution. So there is a clear connection, thanks algorithmic connection here. The centroids don't give much information, as you can see here, except, so the centroids in X and Y, I must say, except for centroids in Z. There you can see a clear knee in the data. And that is also what we saw in this scatter plot before. The relevant information, as we can see, is the area and the Z position. Let's look at that a little bit closer. Let's do the air plot from that one. And we can just see, let's see. No, doesn't want to. Okay. But now we have the information that we want to continue working with. In principle, it's position and size that are the relevant one. So let's look at this. First, we have the label and centroid, or we can also look in a 3D scatter plot where we have label, area, and centroid position. And you can see that it spans out a little bit here. And, well, looks like this is something we could put a nice threshold on. For example, here, putting a threshold, and we would be able to segment it. When you have this kind of data, makes sense maybe to use a clustering analysis. So let's try with k-means. And, well, my code is not completely up to date. That's why I get this error message. But anyway, let's do a k-means with two classes. We only have the two groups. Do a fit and predict based on label, area, and centroid, and group it around, and let's look at some values. So we can see here now that we have another column in our table which tells which group it is. And here is something missing, I believe. Yeah, one. So the clustering did something for us. But if you look at this clustering, it doesn't really make sense because it's really mixing up the two classes. So the problem is that in this case, k-means was misguided. And the reason is that the area is about 1,000 times greater than the other two values. And that is the problem because it will be dominant. And what you see here is actually that when the size is large, it sets that as a threshold in our clustering. So what we do need is, again, scaling. We did that in lecture 4, I think. We did some scaling of feature vectors, and the outcome is quite good. So the scaling we do is now normalization by just centering it and dividing by the standard deviation of the value. And now our result is a nice cut as we expect it to come. And also, we can see that now we have a good separation between the two classes, and I believe this is reasonable actually. Let's look at the histogram of the two classes, and now we come back to what I said when I told you to try to imagine the two distributions. Here we have one distribution, and here you have the other distribution, just as I suggested. So this makes sense. And now we want to assign the value back into the grains, and that is done with the help of a function, again, this gray level reconstruction by dilation. Can assign the labels on each object. And yeah, this loops over all the items and works pretty well actually. And now let's see, that one I just need to execute. Yep. And the result is now that when we have imposed the classes, we can see nicely that there is a good separation between the two classes. This one is probably in the range of certainty, so small was classified as large, so can happen. So this is in the error bounds of the method. That is actually a topic that I'm going to talk about next time. Next week, I understand there is Easter holidays, so we see each other in 2 weeks. And the topic then will be statistics and uncertainties in this error bars on our measurements. And yeah, here 2D, projected in 2D. We can also look at that in 3D, but it's quite messy because we have always the grain gaps between the grains. So if you have, yeah, I think I can show it on this one actually. You can see that the green line goes up because there is a large pore here, and that gives you a quite a spike. And also the blue ones, they go down all the way through here, and that gives you spike in the other region. That is the reason why you get this spiky profile between the two layers. That could of course be estimated on kind of spline surface or some other reduced surface, if you maybe just want to have some cut plane to know if it's tilted. That is up to the following analysis. And that brings me to the end of today's lecture. So I've talked about how we can use skeletons to analyze the topology of our structures. So that is in particular if you have networked structures in your images. And the opposite is actually when you have more compact objects like grains, then you use the watershed segmentation to identify these grains, even though if they are touching. The problem with watershed is that I write here, may oversegment. I would say always oversegment because it always happens. In particular, unless you have very nice round objects, then watershed may not do it. Watershed is very popular, used a lot, and it works in both in 2D and 3D. And it's quite a simple, straightforward algorithm, actually, if you look under the hood. So, yeah, it's convenient to use. And it's also both these two, skeletons and watershed, are available in most image analysis packages. So or just to grab off the shelf, but you may need to do some preconditioning and otherwise noise and misclassifications, they may give you sometimes a bit confusing results. Yep, that was all for today, and I wish you and see you in 2 weeks.